So what's up, guys? We are here now, and I am Reverend Carlos, a student of Holy Angel University, taking a Bachelor of Science in Aeronautical Engineering. So I am here today, and I will teach you how to perform the basic redox reaction, the enthalpy change, final temperature, nuclear decay, and carbon dating. So let's start with basic redox reaction. Now, our problem is boron negative plus MnO negative 4 to MnO2 plus Br oxygen 3. Okay, so that's it. Of course, we will take the first half reaction. Okay, so the first half is T2 Br. Now, the borons are balanced, but the oxygen is not. So we will add water. So plus, by the way, it's 3, so we will add 3 water. 3 H2O. Okay, and then we have 6 hydrogen here, so we will add plus 6 plus. And the charges are not balanced, so we will add electrons here. 6. Now 6, negative 6 plus positive 6 is equals to 0, plus negative 1, so 1, and negative 1, 1, so the energy is balanced. Now let's proceed to the second half. No, sorry, wrong. Okay, so now let's balance the equation first. Now we will add water. So we have 4 here and we have 2. So this side we need 2 more. So plus 2H2O. Now we have 4 here for H, so we will add 4H plus, and the charge, we will add charge now, and it's, by the way, it's 4 minus 1, it's 3, and it's 0. So if it's 3 here, we need to make it 0, so to make it balanced. So we will add 3 negative. So it's balanced. We will now combine. But wait, the electrons are not balanced. So we will multiply this by 2 to make it 6. Okay? So this now will become and this is the new equation for H2O. Okay, 6, 6. And now disregard this because this is the new equation. Now let's cancel this. By the way, to make it clear, I'll just erase it. Okay. Okay. So erase. So that's it. Now, don't mind this. Okay. So 6H plus and 8H plus. We can cancel this. We can subtract this, so this will be cancelled. And this 8 minus 6, it's 2. So if this side is bigger, you will put it here. So it's 2H plus, and this is no longer here. Okay. Now we have 4H2O, 3H2O. So like what I said, this is bigger, so it will remain here. So this is gone, and this will become 1. Okay. Okay. That's it. So now we will combine the equation. So it will become 3 plus 2F4 plus 2H plus this, okay, 2H plus, then we are 3 plus 2MnO plus H2O. So that's the condition. But this is basic redox reaction. So we will add, this is 2H plus, and of course to remove this we need to this. So if we will add it here, we should add it also here. And if we this can be combined, so if we combine this, it will become plus combine 2H3O. Okay, this will become BrO-3 2N2. Oh, by the way, we have 2 H2Os here. We have H2O, cancel this, and this will become 1. Okay, so that no plus 2OH8. So that's it. This is our basic redox reaction. So take a look at it. Okay. So let's now proceed to the second one. So we will now tackle the enthalpy change. So this is the problem. How much energy in kilojoule is required to heat 35.8 grams of water from negative 20 degrees Celsius to 115 degrees Celsius? So these are the guidelines. So ice, water, steam, and change in heat and fusion, and evaporation. Now don't forget the formula. It's mc delta T. So now we will get first the mass of the water. It's 35.3 grams, and then the specific heat, which is ice because it's negative. So 2.06 joule grams over joule grams degrees Celsius, and then the final temperature, which is 20 degrees Celsius. Now, if you'll input this in calculator and multiply it, the answer will be 1,450 joule. By the way, joule was remained because the grams will be cancelled, Celsius cancelled. That's why 1,450 joules to heat the ice to 0 degrees Celsius. Now we are in 0 degrees Celsius. Now let's proceed to the let us now melt the ice in. Let's get the mass of 35.3 grams, and then the fusion, which is 334 joule grams, and answer is 11,800 joule to melt the ice. Okay, let's now proceed to heat the water to 100 degrees Celsius. We will get again the mass, which is 35.3 grams, and then the water 4.18 degrees Celsius, and then the specific heat, the temperature, which is we need 100 degrees Celsius to heat the water into its boiling point. So in this, if you put it in your calculator, the answer is 14,800 joule. Now let's proceed to boil the water. So boil the water, 35.3 grams, and then the evaporation, which is 2,260 joule per grams. So it if you multiply this in your calculator, you will get calculator 79,800. So 79,800 joule. Now let's proceed. So let's proceed to the to heat the steam to 115 degrees Celsius. So we'll get 35.3 grams, and then the specific heat, which is the steam, 2.02 joule over grams degrees Celsius, and then we need the 15 to we get 15 because of 115. So degrees Celsius. If you put this in your calculator, you will get the answer of 1,070 joule. Now we will add this. All of this should be added. So if you add this, you'll get 108,920 joule. And we should divide it in. I multiplied 1 joule over 1,000 joule. So in that, we will get calculator, another 8,920, 1,000. We will get 108.92 Decay. 108.92 Decay. So this is the energy needed to turn the negative 20 degrees Celsius to steam of 115 degrees Celsius. So that's it. Let's now proceed to the third one. So we are now in third one, which is we will solve the final temperature. So this is our problem. A 130 grams of sample of cold water and a 285 sample of hot water are mixed in an insulated thermos bottle and allowed to equilibrate if the initial temperature of cold water is 5 degrees Celsius and the initial temperature of hot water is 95 degrees Celsius. What will be the final temperature? In solving this, we should know the Q of hot is equals to Q of cold. And the formula for this is mc/T. Now for the Q of hot, we'll have the mass of 285 grams and the specific heat is 4.184, and the final temp, the initial temp is TF minus, because we are finding the final temperature. So the initial temperature of hot water is 95 degrees Celsius, equals to the mass of cold water 130 grams, and same with this water, the initial temp is 4.184, and then its initial temp is 5 degrees Celsius. So TF minus 5 degrees Celsius. Now we will multiply these two. So 285 times 4.184 is equals to 1,192.44, and then TF, and we will multiply these two. Why? Because we should multiply it. So multiply negative 95, so it is equals to negative 113,281.8. So that's in the Q of hot. And now let's proceed to the Q of cold. So 130 times 4.184 is equals to 543.92 TF, then multiplied to negative 5 times negative 5. So it's negative, oh, by the way, this is negative. So this is negative, and the answer for this will be positive. Okay, this will be positive. Okay, so the answer is 2,719.6. Okay, now we will combine the without final temperature and the with final temperature. So 1,192.44 plus this, we will transfer it here, so it will become positive 543.92 TF is equals to, and this will be transferred here, and 2,719 plus it's negative, so it became positive 113,281.8. So that's it. We will now add these two. So 2,192.44 plus 543.92 is equals to 1,736.36 TF is equals to, we should add this, 2,719 plus 113,281.81. So it's 116,000.81. And we are finding the TF, so we will stay this, so we will divide it both sides by 1,736.36. 1,736.36. So this will be cancelled. So TF will be remained, and 160,000.81 divided by 1,736.36 is equals to 66.81 degrees Celsius. So this is our final temperature of the mixed water. So this is it. Hey, you've noticed that I don't have the lava gun because it's too hot. So let's start the nuclear decay. In alpha emission, the added is 42He. In beta emission, the 0, -1, B plus antineutrino. And the gamma is 0, -1, B plus antineutrino, 0, 0Y. And the positron emission is 0, 1, B plus neutrino. And the electron capture is in the left side, which is 0, -1, B, and it's neutrino. So now it's alpha emission. In alpha emission, you will just subtract the atomic weight and subtract the atomic number. And 294 minus 4 is equals to 290. 118 minus 2 is 116. Now, you will look in the table of elements, which has the atomic number of 116. So 116 is the vermilion. So the vermilion, Lb. So that's the alpha decay. It's so easy. Now let's proceed to beta emission. In beta emission is 0, -1, B, and antineutrino. And 244 minus 0 is equals to 244. Then 94, this will be plus 1 is equals to 95. Why? Because 95 minus 1 is equals to 94. So the atomic number will be balanced. So let's look at the table of elements, which has the 95. So the 95 is the americium. So its sign is AM. So that's it. It's so simple. So let's proceed to the gamma. By the way, gamma and beta are the same, but gamma has the 0, 0, Y. So 175 minus 0 is 175. And 71 minus -1, and negative times negative is equals to positive. So 71 plus 1 is equals to 72. So 72 minus 1 is equals to 71. So it's balanced. So let's look the 72 atomic number. So it's hafnium. So hafnium is Hf. So it's just very easy. You should just subtract. And let's go now to the positron emission. So positron emission 252, 0. So it will remain 252. And 99 minus 1 is equals to 98. By the way, in positron emission, it is positive 1. So it will become 98. So 98 plus 1 is equals to 99. Now let us look the 98. So the 98 is Californium. Okay, it's Californium. So that's it, and it is neutrino. And the electron capture, the 0, -1, and B sign will be put in this side. Oh wait. Yeah, we will put it in this side because that's the electron capture, and it has neutrino. So the 157, 0, so 157, and 64 minus 1 is equals to 63. Okay, and it is just directly minus because the anode is in here. So the 63 is the europium with the sign of EU. So that's it. Nuclear decay is just easy, and even you can solve this because you only have to do is subtract, and addition. So let's now proceed to the last one, carbon dating. Last one. So the last topic will be carbon dating. So carbon dating, we should first know the K, because the formula of the years. Oh, by the way, the problem is determine the age of the bone if 16.5% of the original amount of C14 is present into the bone. How old is the bone? The half-life of C14 is 570. So T is equals to 1 over K ln NO over M. So that's it. And we have the N and NO, but we don't have the K. But K is equals to ln 2 over T 1 half. So put it in your calculator. K is equals to ln 2 over 507,030 years. So K is equals to ln 2 divided by 5730 is equals to 1.2097 times 10 raised to negative 4. And that's it. Now we have the K, we have the N, we have the O. Now let's proceed to the solving the years. Is equals to 1 over K, which is 1.2097 times 10 raised to negative 4 ln 1 over, since we don't have the NO, we will put it as 1. And the decimal of this is 0.165. We just move 2 decimals, okay? 165. So T is, if you put this in your calculator and solve this in your calculator, the answer will be 1.48 times 10 raised to 4 years. So that's it. That's the age of the bone. That's how old is the bone. So the 5 topics are done, and thank you for watching.